Okay, cyclooctatetraene. Cyclooctatetraene. All right, because there's four double bonds, so it's a tetraene. Um, if you add two equivalents of potassium metal to it, you can actually form this dianion. Now, by looking at that, how stable does that look to you? Yeah, it doesn't look very stable, does it? You have a compound with two negative charges. So before learning about aromatic compounds, you would probably say, yeah, that doesn't look very stable. But you have 10 pi electrons. Let's assume this is planar. What do you guys think? Do you think this can form? Well, it's 10 pi electrons. Does it fit the 4n plus 2 or the 4n? Fits the 4n plus 2. So therefore it does form, okay, because you're forming an aromatic compound. So it reacts with potassium metal to form an aromatic dianion. This is the first time we've ever seen a dianion. Okay, 10 pi electrons, it's aromatic. All right, a little bit of a test. Which of the following compounds is an aromatic compound? All right, look at the two compounds. Let's analyze this. Okay, first thing is one, it's cyclical. All right, so far so good. Two, we do have conjugation. However, what's the issue? The conjugation is not all the way around the ring, right? It stops right here because what's the hybridization of that carbon right there? Right, sp3. I don't have a p orbital, okay? So I pretty much can stop right there, okay? It's also not going to be planar, so I know it's not going to be planar. Remember, you got to look to see if it's planar. The answer is no, it's not planar because of that sp3. So this is a non-aromatic compound. Okay, this compound, let's look at this. Cyclical, yes. Conjugated, yes. Everything is sp2 or has a p orbital. That's actually sp2 also, plus the p orbitals and the plus charge. Okay, is it planar? If we assume yes, then we can go to the next step, which is Huckel's rule. If we assume no, it's not planar, then you stop and say it's non-aromatic. But if it's not telling you, like I said, assume it's planar. Okay? So let's go to the next rule. How many pi electrons? There are 6 pi electrons. Therefore, it fits 4n plus 2, where in this case n is going to equal 1. So therefore, if this one is the aromatic compound. Okay, non-aromatic, there's an sp3 carbon, no, so it's not delocalized. That one, all carbons are sp, that should be sp2 hybridized. I found an error in the notes, the publisher notes. All carbons are sp2 hybridized, and it obeys Huckel's rule. All right. Now here's a situation where you have a molecule that has a nitrogen in the ring, right? This is what's called a heterocycle. All right, heterocycles, there is actually a section, I think, next that we'll talk about, where a heterocycle is a ring that has things other than carbons inside of them, okay? So notice there's a lone pair on this nitrogen, all right? But this lone pair is sticking out of the ring. It's not inside of the aromatic ring, so they kind of show you this, okay? This nitrogen is making a pi bond with that carbon right here, so these two p orbitals are forming the pi bond, and then this lone pair is sticking out of the ring. So it's not part of the pi electron system. This is going to come important when you start seeing things other than carbon inside your ring. So this has 6 pi electrons. So pyridine is an aromatic compound. It's a very stable compound. So pyridine has 6 delocalized electrons in the pi system. The two non-bonding electrons in nitrogen are in an sp2 orbital, and they do not interact with the pi electrons of the ring. They are outside of the ring. Okay, and then they start showing you the pKa's. They actually show you a pKb, but if you just look at the reverse, the hydrogen, this actually acts as a pretty good base. Okay, it's not great, but it will act as a base. Okay, so pyridine is basic with a pair of non-bonding electrons available to extract the proton. If these lone pairs were preoccupied in the pi system, do you think it would be a base at that point, or do you think that'd be a very weak base? it'd be a very weak base because the electrons are preoccupied in the aromatic resonance. They would not be available for a hydrogen, but in this case they are available to a hydrogen, so it actually acts as a base. Okay, the protonated pyridine, or the pyridinium ion, is still an aromatic compound because you haven't done anything to those 6 pi electrons. Pyrrole. Here's the difference. Notice pyrrole has a hydrogen that's coming out of the plane, and it's got a lone pair now. So now this lone pair of electrons, because this is sp3 hybridized, is actually in the pi system. All right, notice in this picture right here. All right, yes, it is sp3 hybridized. So notice we talked about you can't have sp3, you can't have a carbon that's sp3. But we didn't say anything about not having nitrogens or oxygens that are sp3 hybridized. The whole point of aromatic is electrons or orbitals that are parallel to each other that are all the way around the ring. And in this case, you have an sp3 hybridized orbital with lone pairs that in this case are parallel. Okay, so why is it parallel in this case but not the other case? Because the other case I had a pi bond already. So the lone pairs had to be outside of the ring. In this case, I have the lone pairs, which are now in resonance with my aromatic, with the other pi bonds. So in this case, you have 6 pi electrons, 2 from here, 2 here, and 2 here for your 6. And again, you're assuming it's planar, which it is planar. Therefore, this is an aromatic compound. Okay? Even if you had an oxygen here, that compound is called furan. I don't remember if I have a slide about that. I'm sure I will. But just to show you, if you have furan, which looks like this, it's got 2 lone pairs. One lone pair is preoccupied in here to make 6. The other lone pair are outside. Okay? So those as well too. So here's kind of the words. The pyrrole nitrogen atom is sp2 hybridized with the lone pair. It's actually sp3 hybridized. Now, that's not totally incorrect when they say sp2. It's sp3, but because it gets the lone pairs get preoccupied in this resonance, it kind of becomes sp2 hybridized. So does that make sense? So it is sp3 that becomes sp2. All right, it's kind of an interesting type of a phenomenon, and the p orbital is overlapping, and the pyrrole, you know, if you do your 6 pi electron in Huckel's 4n plus 2 and n equals 1. All right, now in this case, it's not that strong as a base. So we saw in the last example that pyridine had a pK of about 8. Pyrrole has a much higher pKb, so it's a much weaker base. Okay, it's a weak base, therefore it's going to become a strong acid when you protonate it, because it has a driving force of becoming a preoccupied lone pair of electrons. These lone pairs of electrons do not want to pluck off a hydrogen that easily off of water to form the acid because they're preoccupied as an aromatic compound. So here's an example where the lone pairs are preoccupied. It's a weak base. Lone pairs that are out of the pi electron are actually much stronger. Okay, so here the pyrrole is aromatic because the lone pair are delocalized. The N-deprotonated pyrrole is non-aromatic because the nitrogen is sp3. So now it's saying that this molecule now is non-aromatic. So you're going from an aromatic compound to a non-aromatic compound. That's an increase in energy. All right, you're going from a more stable compound to a less stable compound, not something nature wants to naturally do. Okay, so here's kind of just to show you that when you have a compound, you can have different types of nitrogens, that the how strong of a base they are. So if you have something like this, like purine, okay, you've got a bunch of nitrogens in lone pairs, but not all of these nitrogens act as a base. Notice these lone pairs are preoccupied in the resonance of this ring right here. All right, and you have 2, 4, 6, 8, 10. You have 10 pi electrons, so that follows Huckel's rule of aromatic. So this is an aromatic compound. So these lone pairs are preoccupied. These lone pairs, these 3 here, the one at the 1, the 3, and the 7, are not preoccupied in resonance, so those can act as a base. Okay. Imidazole is also another interesting one. Same thing. These lone pairs are preoccupied in the resonance. but the lone pairs out here are not. So this is our basic part of this ring. In this case, they both act as a base. Okay, so it looks like I gave you the answer to this one. I didn't mean to. Kind of interesting. So anyways, these are basic, basic, basic. This one is not basic because it's involved in the aromatic ring. Okay, so pyrimidine has 2 basic nitrogens. Imidazole has 1 basic nitrogen. So only one of the purine nitrogens is not a strong base. Okay, and purine is actually found on our DNA. So these nitrogens actually form hydrogen bonds with other things where this nitrogen does not. Okay, so here's kind of the hint they gave you. Practice spotting basic and non-basic nitrogen atoms. Most non-basic pyrrole-like nitrogens have 3 single bonds. It's kind of a clue. If you have all, so it looks like it's sp3 hybridized because it is, but it kind of isn't. Okay, because the lone pair gets preoccupied in the resonance, so it kind of becomes slightly of a sp2 hybridized. The most basic pyridine-like nitrogen has a double bond in the ring, and their lone pairs are sticking out or are sp2 hybrid orbital. Okay, we're going to stop here and talk about other heterocyclic compounds when we come back to the next video.